The dream of quantum computing is being held hostage by its own noise. But what if a surprisingly simple new technique could finally silence the interference and unlock truly reliable results? A groundbreaking new method is doing just that, and it's poised to change everything we thought we knew about error correction. Researchers Alexander X. Miller and Micheline B. Soley from the University of Wisconsin-Madison, along with their team, have introduced a powerful new tool called the Random Inverse Depolarizing Approximation, or RIDA. This innovative approach tackles the single biggest hurdle in quantum computing today, the crippling errors that plague current-generation hardware, known as noisy intermediate-scale quantum (NISQ) devices. Unlike existing methods that often make complex assumptions about the type of noise or demand enormous computational power, RIDA offers a beautifully straightforward and universally applicable solution. It works by cleverly estimating how much a quantum signal has been lost or depolarized due to noise, and then uses that calculation to recover the pristine, correct result. But here's where it gets controversial. The study presents a head-to-head competition between RIDA and the current leading error mitigation techniques, namely exponential zero-noise extrapolation, ZNE, and a method using only CNOT gates. The results are not even close. Across the board, whether using more qubits or simulating higher error rates, RIDA consistently delivered superior accuracy and far greater robustness. Its performance doesn't fall off a cliff. As systems get larger and noisier, it degrades gracefully, suggesting it is fundamentally more scalable. And this is the part most people miss. RIDA achieves this higher accuracy while being far more efficient, requiring significantly fewer measurements, or shots, to reach a reliable answer. This is a huge deal for practical applications where time and access to quantum hardware are limited and expensive. The researchers didn't just run simulations. They also provided strong analytical proof for why RIDA works so well, and their math perfectly matched the real-world numerical results. In stark contrast, the older methods showed their limitations through unstable V-shaped error curves, a telltale sign that they are struggling to accurately model what's actually going wrong. Now for the provocative question. If RIDA is this effective and efficient, does this render previous error mitigation strategies obsolete? We're opening the floor for debate. Let us know your thoughts in the comments. The implications are enormous. By providing a practical and robust way to mitigate errors, RIDA could be the key that finally allows scientists to run more complex and meaningful quantum algorithms on the imperfect hardware we have today, not just the fault-tolerant machines of the distant future. This opens new doors in fields like materials science, where simulating complex molecules is crucial, and physics, where modeling quantum systems is paramount. The team has even made their RIDA code open source, inviting the global research community to build upon their work. So what's next? The future of this research is incredibly exciting. Scientists will need to test RIDA on actual quantum hardware with even more qubits, probe its performance under different types of error models, and explore hybrid approaches that combine it with other techniques. One fascinating avenue is developing adaptive strategies where RIDA's parameters automatically adjust in real time based on the noise it detects. By efficiently approximating the probability of depolarization isn't just a plain incremental step forward. It offers a genuinely promising pathway toward taming the chaos of noise and finally realizing the immense potential of near-term quantum computers.